Bennu, 63 million miles away. You begin to approach it. You begin to, start scanning for landing sites, and you ultimately landed on a site known as Nightingale. But before you picked that site, you guys were thrown a curveball because you realized that it was not as smooth as you had expected.
Yeah, right. So someone had failed to tell Bennu how it was supposed to be for us. Right. So if you looked at early artist conceptions of the whole sampling system, you'd see this animation of the spacecraft coming down, and a sampling a fixture would be pressed down against this sort of rounded beach of looking sand, nice and smooth. And there'd be a little puff of dust, and then it would back up with our sample. But when we got there, we found out that the surface was just utterly covered from one end to the other with boulders of all sizes up to houses. And so there were no easy, smooth, soft-looking places that were obvious to land. And we have a constraint on our sampler. The way it worked is we couldn't really grab and ingest stuff bigger than a couple centimeters in size. And so we needed a place that was predominantly covered by small rocks and dust, not boulders. And so the initial idea was the hope that a good fraction of the surface would be available for us to consider sampling at. Well, instead, we ended up having to do a great deal of work to more or less search every square meter of the asteroid, looking for places where we thought we had a good chance of succeeding in capturing sample.
And whether it was intended or not, I'm sure it was intended, but that resulted in some beautiful imagery of this beautiful asteroid that's got this sort of egg-like shape. You'd say
it's here. This is its shape.
Oh, well, there you go.
So this is a 3D model one of my brothers and I printed. And so you can see some of the boulders that are the sizes of houses. This whole thing, its dimensions is about a half a kilometer.
Yep.
So it's big, but not that big compared to many other asteroids. And it's kind of an oblate spheroid. You can see it's more or less round, but it's got this sort of ridge around the middle that bulges out a bit. And so we had designed the mission. We knew that it was already pretty much in an orientation like this, rotating every 4 hours, and that almost the entire surface would be in the sun at one point or another during the rotation, which is, we're just really lucky the way the axis was oriented. And so the plan was to take pictures at multiple scales of the whole asteroid. So that gave us and we also had a laser altimeter on it board. So that let us make a very precise shape model of the whole asteroid. So we know where the rocks are and the boulders. And then we had to go through all of those images and all that data, trying to find a good place where all these big boulders aren't in the way. And there was a surface that was smooth enough and dominated by small enough material that we could actually have a good chance of going down and getting the sample successfully without risking the spacecraft's safety.
Now that bulge at the equator there, is that is that a byproduct of the way it was formed, or is that something more due to gravitational forces like we see on Earth?
It's a couple things. So first of all, we know this is a rubble pile asteroid. So this is not a big rock with some little rocks on it. It's probably just a jumble of small rocks all the way down. And it is probably the reaccumulation of material that was blown off a much bigger parent body in the old ancient days of the solar system. There was probably a much larger parent body, probably 20 to 50 times bigger than this, that was broken up into pieces, and some of those pieces reaccumulated to make Bennu. And so since it's made up of just a jumble of rocks, it doesn't have a great deal of rigidity. It doesn't have a lot of internal strength. Mm-hmm. And so most of these rocks and the gravity on the surface of this body is really almost negligible.
Right.
If you were on the equator and you did a nice vigorous push-up, you'd probably just throw yourself right off the asteroid.
Right.
So what that means is that most of these rocks are not nailed down very well, and so they're easily made mobile. And since this thing is rotating pretty fast, every 4 hours it goes all the way around. There's a tendency for material that is disturbed to want to move towards the equator, like on if you're on a merry-go-round, right? There's that.
Right.
It's trying to throw you off the merry-go-round. So material probably over time migrates this way. And so we've built up this belt here in the middle, which is probably consists of a large amount of material that has moved down and up from the poles. to this position. So it's a combination of rapid rotation and weak gravity that's probably defined most of this shape.
Right, and that weak gravity in rubble pile eventually was a bit of an issue when you collected your sample. But before we get to that, and before there was touchdown, correct me if I'm wrong, OSIRIS-REx, it holds a couple of interesting records and facts, but one of them being that it is the closest orbiting man-made object to a celestial body at points, right between 1 and 2 kilometers.
Yeah, and we know that because it's in the Guinness Book of World Records, so it must be true.
Yeah.
But yeah, since its gravity is so small, in order to get in a stable orbit about it, we had to get really quite close. And so that's one of the main reasons we hold that record, is that an orbit wouldn't even be possible if we were very far away, because the gravity wouldn't be strong enough to hold us with the asteroid. So it required, the mission, these missions only work because you have a large number of people who really know their stuff in a lot of different areas. And
right.
our navigators did a super job of getting us there, getting us around the neighborhood while we were there, and then getting us back. And all these maneuvers required a high degree of precision to pull off.
Can you speak to the technical nature of the actual? I'm curious about the propulsion system. When you're adjusting, going closer and back and forth, are these cold gas thrusters, or are you?
Yeah, so the delta, the velocity changes required are really incredibly small because you're not in much of a gravity field. So you just use small thrusters to give yourself little pushes that just modify your orbit, and then you let time get you where you want to be.
Right.
And so there were a lot of propulsive events, but they're all very subtle things.
Right. So relying heavily on Newtonian physics.
Taking off from the pad.
Right. Exactly. So bring us back then to the day of touchdown. So the way that this was going to work, OSIRIS-REx has the TAG-SAM, the touch and go specimen acquisition mechanism. It's kind of like a punch hole, or a hole punch, depending on what part of the continent you're on. And tell us about that. How did that mechanism work? And
well, so the way it worked is we had a long arm that hung down below the spacecraft, and that was the only part that really touched the asteroid. And at the bottom of it was a disc about this big around, and the disc had within it a round filter, kind of about the size of an old-fashioned air filter on a V8 engine. And the idea was, as this pad came in contact with the ground, we opened up a valve that let pure N2 gas, nitrogen, flow down and out of some nozzles, and they would stir up the material underneath and mobilize it so it's flying around. And some of this material would go up and hit a deflector plate that would then shoot it sideways through a kind of mylar flap, like a cat door kind of, that went all the way around this. And then material would get pinned up against this filter area and captured. And then the idea was that when we were done and the gas stopped flowing, these flaps would fold down and all the material would be captured in this ring.
Interesting. This just occurred to me, and I am no space engineer at all, but would something like a centrifuge inside a collection mechanism help to concentrate the material on the outside so you could collect more?
We used the gas flow to do that. So the gas flow was supposed to go up and out through the filter. That's why it was a filter instead of just a metal plate or something. If it had been a metal plate, we would have pushed gas in there, and then the back pressure of that gas would have pushed back on us, and it would have kept other material from going in. So we wanted the gas to flow down and then up and out to collect stuff. And anyone who watches the actual footage of us doing this realized that a lot of this gas didn't just push stuff up and in, but also push stuff out and out, all over the place. But fortunately, the system worked well enough to get us more than twice as much material as we needed to get to meet all our science requirements. So it did everything we needed it to.
Right. You were shooting for about 60 grams and ended up with about 22 grams in total. Mm-hmm. Now, what I found fascinating in following this is that when the touchdown happened, and I don't think that you guys expected that 6 tons approximately of material was ejected when this happened, and that was due to the loose rubble nature of the asteroid. I heard somebody describe it as being almost like a foam, that if you were to step on the surface of Bennu, you might actually sink a considerable amount into it.
Well, if you had velocity to push you in, but the
Right.
gravity itself wouldn't pull you in. But
Right.
so I should correct something I said earlier that if you're at the equator and you did a push up, it would throw you
Hmm.
off.
Hmm.
That's only if you could actually do your push up against the surface. But as what might happen is you might push down with your arms and find out you just pushed your arms
Right.
into,
Right. Right.
into the surface, and you're still there. Yeah. So I mean, I guess I wasn't surprised that stuff went flying everywhere. I mean, you can do a simple calculation of energy, how much energy is contained within the gas bottle under pressure,
Hmm.
and how little gravity there is holding everything together, and then take some estimates of the mass of the rocks and do a calculation, and you quickly find out you have enough energy there to mobilize massive amounts of material. So I wasn't sure exactly how it was going to look, but I wasn't the least bit surprised when things went flying everywhere.
Right. Right.
And as long as that stuff flies away and doesn't harm the spacecraft, and that we collect the sample we want. And since I'm largely in this for the sample, I was a happy guy. But in addition, the fact that you launch stuff actually could be used to do other science. You could see where this stuff, went, and it gave us a good indication of how weak the surface really is. So.
No, actually, that does actually answer one of the questions that I had, which would have been: were there any precautions in advance to prevent OSIRIS-REx from altering the trajectory of Bennu?
Yeah, so the same energy calculation tells you that the actual push was absolutely negligible. Okay,
Right, right.
we didn't affect its orbit in any particular way at all. Uh, the forces involved with our sampling are just trivial compared to the mass of the overall asteroid, and so Bennu's trajectory is actually being modified more by the pressure of sunlight on its surface than by the OSIRIS-REx spacecraft encountering it.
Right.
And in fact, that's one of the things we measured is that that the Bennu asteroid its orbit is in fact evolving just because of pressure from solar radiation and the effect it has on the surface.
Now, the reason why I was going to ask that question is because there was a time when Bennu was thought to maybe be a impact threat on Earth, and so the trajectory might be an important thing. Is it still considered a threat?
Oh yeah, it's on a trajectory. It's an Earth-crossing asteroid, and so it crosses our orbit every few years, and there is actually a period starting in about the 2130s, I think, where there are small chances that it could hit the Earth, and this goes on for a number of decades before its orbit evolves on to where it's not really a problem anymore. It's never a big threat. I think the highest odds for any of these is like 1 in 10,000 or something. But this is also one of the reasons we picked Bennu to go to, is because since it was on the hazards list, it made good sense to go there and characterize this object so we understand it. And our effort, gave us a much better understanding of the orbit, so we can be do a much better job of trying to understand whether it ever might hit us. And then also, if it turns out that we think it might, we'll really understand this body, so we'll know much more precisely what we should do about that. So it's not a hazard now. It won't be a hazard for us. But our grandchildren might be paying attention just to make sure it stays that way.
So let's fast forward then and sort of look back at the return. Right, this is OSIRIS-REx, I believe, was the second fastest man-made object to enter the atmosphere at 43,000 kilometers an hour, which is an incredible amount of energy that needs to be dissipated with its ablative shield and that sort of thing. And you were there in Utah, waiting for it to make impact, a gentle impact in the desert of Utah, about 500, 600 square kilometer target. And you were one of three people who were there to say hello, to greet back.
Well, there was more than three. I mean, we had a couple of helicopter loads of people. There's some pictures where there's three of us there, the three of us who were some of the first to approach it and to check out the state of the SRC, the sample return capsule, to make sure it was in good shape. Because if it had come back and was damaged in any way, then we would want to follow procedures that made sure that we did everything we could to maintain the pristine nature of the sample. But the capsule actually touched down pretty much perfectly. I mean, as you've seen the pictures, it's like actually balanced on its nose cone, which was surprised the heck out of me when I saw that.
You can see in the sand the way it rolled like a top.
Yeah, well, so there's a couple pictures. You're probably thinking of the Stardust one, maybe, but when Stardust came down, it was in a crosswind in the middle of the night in a snowstorm, and it hit moving sideways.
Yes, that's right.
And so it hit and it bounced and flipped, and it hit and bounced and flipped, and it hit and then eventually ended up on its edge and rolled for a while like a quarter on a desk, and then it finally laid down on its side.
Right.
And it did go in a circle at that point. You can see in the mud the circle as it went around in a.
That's the image I was thinking of.
Yeah. Right. So OSIRIS-REx came down during the day, which made it a lot easier. There was no storm, which made it a lot easier, and it came down on its parachute almost perfectly vertically. So it came down and it hit on its nose cone and it bounced up and landed on its side and then just rolled back onto its nose cone. So it rolled back into the original divot. And so it had a little cup after it hit, and when it impacted, it crushed enough soil down to make a divot, and it rolled back into that and balanced. And so when we first got there, I thought like, okay, who's been messing with the capsule and tipped it up on its nose? Because that's not a stable way for it to be. But when you went and looked very closely, you could see the divot where it landed on its side and then just tipped right back in. So it was a very elegant landing. If I had been holding a card up, I would have given it at least a 9.9. And that also meant that the capsule was not put under any particularly additional stresses associated with breaking any seals or causing anything to have the potential leak. So this meant our sample was inside, nice and safe, completely uncontaminated by any of the local soil or vegetation or anything else. And so it was a really excellent touchdown.
I love the video of the sample canister closing up and the whole return capsule getting ready, to leave Bennu, and I can't help but think, oh man, what a crazy gasket that must be. The plumbing in your kitchen, oftentimes the gaskets, they just go, or you can't get it to work properly. But what incredible engineering is involved.
Yeah, I mean, a lot of testing there, and we did have some advantages that many aspects of the capsule for Stardust and for OSIRIS-REx were very similar. So we had a lot of testing from the Stardust capsule that helped us with the OSIRIS-REx one. But the actual details of the sampling mechanism and how it had to be contained and so on were a bit different. So on Stardust, we had no camera that could take pictures of the whole thing sealing up. So we weren't really, we had various sensors that said it all worked fine, but there was still a little bit of residual anxiety in the back of our head that when we entered the atmosphere, was everything really the way it was, tightened up the way it was supposed to be. In the case of OSIRIS-REx, it was lovely because we could see the sample canister collector being put into its holder, seeing all the detents clip onto place, see the arm pulling out, and then watch the whole clamshell close up and button up tight. So that was great, gave us a lot of extra confidence that everything was ready to come back. We did also see some, when we were clipping the collector in place, see some particles drifting out. So we knew we were losing a little bit of sample. So that's one of the reasons we decided to close up more quickly than we might have otherwise, is because we didn't want any of the precious stuff we'd grabbed to get away.
Of course. So which of the two events, in your opinion, launch or reentry is the more stressful one, or an enjoyable stress? Which of those is more memorable to you, I guess?
So since I'm in this for the sample, I guess getting it back in my hands, so to speak, is maybe the most visceral one. I mean, the launch is impressive because of the sheer power of it. I mean, it's impressive to be miles from the launch pad and feel your whole body vibrating because of all this energy that's being expended. But I've had a feeling just a couple times in my life that's a little hard to describe, but one of those times was when the Stardust capsule came back, and you just suddenly realize that, amazingly enough, you're kind of participating in a bit of history. I mean, Stardust capsule was, I believe, the first thing made by humanity to leave the Earth-Moon system and come back, and here I am on the team picking it up,
standing right in front of it
to get it back. And so most of the time you're busy working. You've got a lot of things to do. You've been practicing them for months, and you're getting on with the job. But every now and then you get a little bit of time to be, retrospective, like when you're in the helicopter flight heading back to the main site, where you get a moment to reflect, and in which case you do kind of have a interesting gee wow kind of moment.
I could only imagine.
And so I had the same feeling on OSIRIS-REx. Maybe it was a little less intense because I'd been through this before, but it was still a very real, very visceral thing. I mean, you look at the capsule and you just think, the places you've been.
Right. Yes.
The things you've seen.
Amazing. And I mean, a little bit of delayed gratification because you could not open that capsule right away. It took months for you guys to
we had to be really patient, but we practiced that by being patient for the whole mission, right? So as a sample return person who's interested in the sample, you have to be patient because you've got to get through all these things. You mentioned how there's these various stress points along the way. Well, the sample scientist gets to enjoy all of those because anything can go wrong up to the very end. If you're someone who's taking images of the asteroid, at some point you've got all your images, and if the failure happens after that, you still have everything that you needed to do your part of the effort. But for the sample scientists, everything needed to work right up to the end. So it was a little frustrating waiting to get everything out, but on the other hand, we'd already done a lot of waiting, and also we knew the sample was there. We knew we were going to get it. It was just a matter of time. So we just had to be patient for a little longer.
Couple of more sleeps, right? Now, before you could get into it, you guys ran into an issue with some screws that were essentially stripped because of the fact that you collected so much material. Can you tell how you guys got around that problem?
Yeah. So, it wasn't because we had too much material. It was because of a self-imposed restriction we had on the tools that were allowed in the glove box. So the sample went into a special glove box that was purged with nitrogen so we could keep it pure while we were disassembling everything. And one of the ways to limit the kinds of contamination you could have in the sample is to restrict the number of things and the kinds of things that could be in the glove box. I mean, you can't get contaminated by something that isn't allowed to be there. And so we had made a conscious decision that we would only allow a certain list of materials to be inside the glove box. And one of the things we didn't want to have is 18 different kinds of steel and aluminum in there, all of which could potentially contaminate us. So we made special tools out of a limited set of metals for things like the screwdrivers that remove the screws. And so normally when you use a screwdriver in your garage, you're using something that's got is made of steel, which is designed to be very, very hard and to be able to handle any screw. And so if you have problems with screws, it's usually because you stripped the screw head, not because you wrecked the screwdriver.
Right, yes.
But we made screwdrivers out of a limited list of metals and discovered that some of the screws had gotten tight enough, either from during their installation or just from flight over time. Metals do vacuum weld, for example, with each other, that the screws were set in there hard enough that when we tried to use the screwdrivers we specially had built, that the screwdrivers themselves were the things that were starting to bend, not the screws. And in either event, we wouldn't want either one to be deformed because that would have the potential of getting little bits of that metal out as a contaminant. Right. So we got most of the screws off. We got down to the last two and found out that every screwdriver we were trying to use was starting to deform. And so we thought we'd got to stop. Otherwise, we could contaminate the sample with screwdriver. And so that required we back up and think about our materials again, find another material that we decided was acceptable to be introduced into the glove box and get screwdrivers made out of.
I see.
That material, that harder material. And then once we had that, then of course we needed to practice it on engineering models to make sure it would all work. We're not going to go test out a new idea on the actual sample container. And then once all that testing was successfully done, then we could go back and do it. So this took some time and the development of some replacement tools, but it worked.
Back to OSIRIS for a second. And the beautiful thing about your mission is that it's not over. OSIRIS-REx is now OSIRIS-APEX, and the spacecraft is moving towards a second asteroid, Apophis. Can you tell us a little bit about the second half of this mission?
A little bit. I'm not deeply involved with that. Since I was the sample guy and the samples are on the ground, my activities moved elsewhere, but I can tell you a few things. So after we got the sample, we headed the spacecraft back to Earth, and we now needed to deliver the capsule, but we didn't want the whole spacecraft to crash into the Earth. So what we did is we aimed the spacecraft at just the right position on the Earth's limb so that we could kick the sample return capsule loose and send it towards the Earth. And then the spacecraft itself was diverted so it wouldn't crash into the Earth. And we used the Earth's gravity to give us a gravity assist to boost us into, or to push us into a new orbit that'll take us to Apophis. And so while the sample return capsule was coming down in Utah and I was rushing out to greet it, the spacecraft itself was passing the Earth and heading on to a new phase. Now, in that new phase, it doesn't have a sample return capsule anymore, so we can't go to another asteroid, get another sample, and bring it back. But we can visit another asteroid and use the onboard instruments to study it. So we can use cameras and our infrared spectrometers and all these other instruments to take data from a whole new asteroid. And so we can learn something about another object that wasn't on our original requirements list. So this is all, kind of bonus science. We didn't have to launch a whole new mission to get to Apophis. We're able to take a slightly used spacecraft and do the task. And so it's a great way to get more bang for our buck. And so the spacecraft's on its way to Apophis. Apophis is a different kind of asteroid. It's, instead of being a very dark, low albedo object like a carbonaceous chondrite, it's a much brighter object. So it's probably more akin to the kinds of meteorites we call ordinary chondrites. So it'll have considerably less organic stuff in it, largely be made of rock. And it's also a funny shape. It's very elongated. And so it's possible that elongation has come about because of tidal stresses from passes of the asteroid by the Earth. And so people want to look into that. So there'll be a lot of interest in the surface of this body and its overall shape. And then we'll learn something about its composition from the onboard instruments and so on. And we won't learn the level of detail we're learning from Bennu because we have the sample in hand, but we'll still learn a tremendous amount. And like I say, all of this is extra science we're getting without having to build a whole new rocket and a whole new spacecraft. So it's great.